Welcome back. Let us resume our discussion on the noise analysis and try to make certain other conclusions out of it regarding the sizing of the devices and the conflict with other design optimizations related to the bandwidth and the gain. So we look at the noise contribution of the three devices, the M1, M2, and M5. We have, of course, not looked into the noise contribution of the tail current source, and we have not looked into the noise contribution of these two. The analogy with the tail current source is that the noise contributed by the tail current source, it's going to be divided equally into the two paths. So if you are looking at the tail current source, whatever noise is produced by the tail current source, it is going up the two paths, and is going to result in equivalent voltages at both the nodes, and in a fully differential operation it will be cancelled out. Therefore, we do not worry so much about the tail current noise contribution. So this is one point that we need to keep in mind. So basically, the two paths or the two noise signals that are going up this channel and then getting folded and going out to the differential output, both these sources are correlated. So if I assume that these are the two noise currents produced by this GM 1 square, whatever, I guess it was 5. Let me see the number. So I guess 6. This was M6. So GM6 square, VG6 square. That is going equivalently divided into the two branches and getting folded down. Therefore, these two sources are correlated, and when you take the differential output, it is getting cancelled. So its effect is not appearing significantly in the differential output. So we ignore the contribution because of this gate noise as well as the channel current noise. Another important factor is we are using the differential operation only to figure out the overall noise, and the main issue there is that when we look at the noise signals at the two gates, they are uncorrelated, they are independent. So whatever input referred noise we calculated, they are coming from the two different branches. Each of the devices are having different noise contributions. They are uncorrelated. So the two noise signals over here are uncorrelated. If we magnify these two noises, they are going to result in some random noise signals at the two gates. And as a result, if I want to define the overall noise signal at any instance, so at any instance we can find out what is the instantaneous noise voltage at the positive input, what is the instantaneous noise voltage at the negative input, and the difference of that gives you the differential input. So just like we do normally for a differential amplifier operation, any arbitrary signal can be broken down into common mode and differential signal. Common mode signal does not get significantly amplified, only the differential part gets amplified and appears at the output with a much magnified response. Therefore, we are considering only the differential response, and doing that we look at this as an AC ground and then figure out the total output referred noise and the input referred noise. So this is another point we should be taking note of with respect to the overall analysis. Now let us try to answer another issue which deals with the noise contribution of these cascode devices, the cascode PMOS and cascode NMOS. So I can look at both the noise contributions, the gate noise, the flicker noise, which is modeled as a series voltage in the gate, and the second one, the channel current noise. So I can just look at the NMOS condition, and the results will be similar to the PMOS. So for the NMOS, I have a large impedance RD in the drain, right? So if I'm considering the M3, it is seeing a large impedance into the drain, which is GM RO times RO. So I can call it RD, which is a large value. Likewise, M3 is also having a large resistance in the source, which is RO. So I can call it RS. So of course, RD is much greater than RS in this condition. And then on the top of that, we have the noise contribution because of this channel current, if we can assume it. And then you have an overall signal, the noise signal at the gate. I can call it VG square, I can call it V channel square, VCH square. And because of this, I would like to find out what is the overall output voltage over here. Now if I here I cannot directly translate this VCH square divided to equivalent gate voltage, because for this case the source is not ground, not an AC ground. As a result, I cannot directly divide this ICH. I cannot divide directly this ICH square divided by GM square and get a equivalent gate noise voltage. That can be done only if the source is grounded. And therefore, let us first consider the Vg square. Now, if I consider the effect of Vg square and find out what is the output noise because of Vg square, this is our common source amplifier based source degeneration, and therefore definitely the overall gain from this input to the output can be written as GM of this device, which is, I guess, GM3 square times the RD upon GM3 RS plus 1. This is approximate expression. This is not exactly true when you are having a very large impedance connected. You get a slightly different expression over here, but approximately I'm writing the same expression. So you are having, GM3 RD square upon GM3 RS square. This is the overall gain. And once again, if I assume that GM3 RS is much greater than 1, which is true here, so I'm getting RD square upon RS square, and therefore we can see in this case you are reduced to GM square RO 4 upon GM square RO upon RO square, and therefore you are having an overall expression GM square RO square. And now if I look at the input referred noise, this needs to be divided by the overall gain, which is GM RO whole square. So VIN square, because of this, is going to be VG square times GM square RO square divided by GM square RO square whole square, and therefore this is going to be VG square upon GM square RO square, which is significantly smaller contribution, much smaller contribution as compared to other devices. Even at the output, if I look at it, if you consider the for example input device or the devices which are connected to the sources, their VG square is directly getting multiplied by the gain of the amplifier, which is GM square RO square. So there you are having a multiplication factor which is GM RO whole square, whereas the contribution of this source is lower by a factor of GM RO. So if I am considering VG, it is getting only multiplied by GM RO, whereas if I am considering the gate noise voltages of the devices which are connected to the VDD and ground, in our case the M2 and M5 and M1, their noises are getting multiplied by GM RO whole square, and as a result the noise contribution of these two can be ignored as compared to the noise contribution of M1, M2 and M5. This is one effect. Likewise, I can look at the I channel. What is the result of I channel's contribution? So intuitively we can see what is going to happen if I assume I channel to be increasing or decreasing in a certain direction, right? So if I assume that I channel is a random current and it is go up or down in a certain direction, ultimately it is going to subtract from the channel current. So assume that you are having a fixed current IDC, and on the top of that you have this randomly fluctuating I channel. It can go up and down. Suppose at a certain time instant it goes up, that means the current is positive, the I channel is positive, flowing from drain to source over here, and therefore it will increase the source potential, right? So if there is an increased channel current, it will try to increase the source potential over here because of this R coming in, RS coming in. Sorry, I did not mention RS, so if you remember, this was RS and that's what I've used. So if I increase the I channel at a particular instance, that will increase the the Vs over here. Vg is a constant potential. When I'm analyzing the effect of the AC channel, Vg is AC ground constant potential. As a result, when your source potential over here goes up, it is reducing the VGS, and therefore it will suppress the increase in the current. So it will whatever assumption I took in the beginning, that because of the noise there is an increase in current, and that is causing this increase in source potential, that will lead to reduction in VGS of this MOSFET, and that will suppress that current. So we are having kind of negative path and is cancelling out any increase. So that this kind of negative feedback kind of is going to suppress the effect of I channel in this case. Same thing is true for VG also. That can also be explained with the help of this negative feedback. So ultimately, when we are talking about a source degenerated common source amplifier, that negative feedback action is present. So VG going up it will try to increase the channel current, and that will try to increase the voltage at the source of this device, and that will reduce the again VGS, and hence try to suppress the increase in the channel current. So this negative feedback mechanism present in the cascode device, it's helping us in reducing the effect of noise contribution of these devices on the output, and hence the input referred noise. Therefore, we are ignoring it. And analytically also, we can try to, in this circuit, we can try to solve the KCL and figure out what is the expression for I channel. We can do that very quickly. If I look at it, if I look at this model, so assume the VG is 0. So MOSFET gate is 0. Gate potential is AC ground, and therefore I don't. I can look at the GM VGS term. You have the RD, which is between the drain and AC ground, and you have the RO, and also you have the RS over here. We know that RD is much greater than RO, much greater than RS, and here you are having the GM VGS definitely, and apart from that you also have the noise current, which is 4 kT gamma GM. It is not dependent upon the VGS, it is just a constant term which is having some RMS amplitude, so we can call it some constant times GM. So this is 4 kT gamma GM, this one, and this is your GM VGS. VG is anyway 0, so it's just GM times VS, and then based on this we can figure out what is going to be the output potential over here, V out, and that is going to give me the exact expression for the V out dependency on the current produced by the channel noise. Now if I assume that this is Vs, the unknown voltage, and this is Vd, at a particular instance we can assume that there is some polarity. Of course, overall the noise current is random, it is not having any polarity, but for a particular instance we can say that okay, it is spiking up, and as a result the current is in a certain direction, and therefore let us see that if the current is in this direction given by the magnitude 4 kT gamma GM, peak amplitude times some constant, of course, depending upon the frequency of integration, and these are this is the value which is GM VGS, is just GM times VS, and remember that this is the current over here is supposed to be the root of this quantity. So this is the current density, the mean square value IN CH square, and when we add it we have to take the root under GM value. So root under GM times the bandwidth, as we say. So let us do it. Let us call it root under GM. So some constant and root under GM. This is GM VGS, and then we can figure out what is going to be the effect of this noise current I channel on the output. And let us look at Vs first of all. So Vs upon Rs is the current flowing in, that must be equal to the current going into the circuit. So I can call it minus V out upon Rd. So I can express Vs as Rs upon Rd minus times V out, and then I can write down the overall expression for current over here, which is root under K0 times GM, which is the current just dependent on GM, plus GM times VGS, which is 0 minus VS, plus you have V out minus VS upon RS, RO. This should be equal to Vs upon Rs. This is the expression we have finally, and I can solve for Vs. You have K0 times GM root under plus Vs I can basically replace by V out and then solve for it. So you have minus GM minus 1 upon RO times Vs, which is you get Rs upon Rd times V out over here, plus V out upon RO, and this is equal to minus again Rs upon Rd upon Rs times V out, and then you can cancel out. We are now I can take this on the other side and find out the expression for V out. So V out is going to be given by root under K0 GM divided by, with the minus sign, divided by 1 upon Rd, 1 upon RO plus Rs upon Rd, times Gm plus 1 upon Rho. This is the overall expression I am getting for the V out. Magnitude point of view, I will look at the mod of this quantity only. And now if I look at these quantities in the denominator, I can take some simplification based on whatever assumptions I had. So I know that Rd is much greater than Rs, and therefore this quantity is much smaller than 1. And then you have the Gm and 1 upon Rho. Out of these, again, I can ignore the 1 upon Rho terms, because in general I am assuming that it is much smaller than Gm. And among these two numbers, 1 upon Rd and 1 upon Rho, we know that Rd is much greater than Rho, so I can ignore the 1 upon Rd term. And now if I look at Rs and Gm, so in the denominator side I have 1 upon Rho and Rs Gm. So Rs is just Rho, so you have Rho Gm upon you have Rd, which is once again large, which is Gm Rho times Rho. So I am basically left with 2 upon Rho in the denominator and root under k naught Gm over here. So root under k naught Gm and 2 Rho is or Rho by 2 is what we are getting. So root under Gm Rho by 2 and k naught is some constant number. So the constant terms are going to determine my overall unit. So we can see that the magnitude point of view, it is this is the noise term 4 kt comma Gm times Rho. So this voltage once again is proportional to the root under the Vn square, because or ICH square. So I can call it ICH times Rho upon 2. So this is basically nothing else but expression for ICH. So ICH times Rho by 2. So this is the overall voltage I am getting. So I can call this ICH. This is the channel noise current magnitude times Rho by 2. And then if I want to refer it back to the input, once again I will divide this quantity by the Gm Rho whole square. So here itself, at the output point, I can compare what is happening. So if I talk about the I channel of the other MOSFET, if I talk about the I channel of say, if I talk about the I channel of the M2, or I talk about the I channel of M, and then getting multiplied by Gm square or Gm Rho whole square. So if I look at the magnitude ICH times Gm Rho square. So if I compare this, try to contrast this with the channel current effect of M2. So INCH2 is getting divided by Gm2 to give you the gate noise voltage of M2, and then it is getting multiplied by Gm Rho square. So basically I have ICH2 getting Gm times Rho square, whereas the ICH of the cascode device is just having a factor ICH, call it 3 times Rho by 2. So here you are having Rho by 2 and here you are having Gm Rho times Rho, right. So magnitude point of view, once again the same conclusion, that the overall noise voltage at the output because of the cascode device is Gm Rho times smaller as compared to the devices which are connected to the VDD and ground, that is the M2 and M5. Therefore, as compared to the noise contribution of the I can call them common source devices, because their sources are grounded and their noises are contributed in the form of a common source amplification. As compared to those devices, the cascode devices noise are lower by 1 upon Gm Rho factor, and therefore I can ignore them. So this is the analysis just to conclude this result. Now once we have concluded that and we look back at this expression over here, we can again correlate it back to the analysis that we did with respect to frequency response and try to see how these two requirements are conflicting: requirement of lower noise and requirement of higher bandwidth and good gain, if at all there is any conflict. So before we go further, any discussion on whatever we did with respect to the noise contribution of cascode devices? All right. So let us go back and look at the expression that we had for the overall output referred and input referred noise because of the main contributing devices, and also look at the corresponding frequency response analysis that we did with respect to these capacitances. So here once again we can see what is going to happen if I choose the device dimensions to minimize the noise. And one of the important factor that we mentioned in the beginning, I need good GM for minimizing the noise, and for that I need large W by L or W1 of M1. Therefore, a large W1 of M1 is definitely going to make the CGD1 dominant. It is going to increase the CGD1, which is going to contribute to this pole. Larger L5 and L6, as I said, it is not going to increase CGD5 significantly, because CGD5 depends upon the overlap capacitance. So, CGD is dependent upon the L overlap, which is the constant parameter for a given technology, times W. Therefore, it does not suffer or does not increase when we are trying to apply larger L5 or larger L2. I should call this 2. It's not really L5, 6. It should be 2, because L5 or L2, because this is the bottom device we are talking about. So, L5 or L2. So, increasing the L5 or L2 it does not really increase their CGD significantly. As a result, it does not have a significant fight with the compensation. And another factor is that the cascode devices are not contributing significantly to the noise, and therefore, I can bring their W by L ratio down significantly without sacrificing my noise figure, and as a result, the CGS4 effect can be minimized. So, that is not going to play a very important role. So, the main contributor is going to be CGD1 at this node, and therefore, even for the differential response as well as common mode response, the non-dominant pole at this point is going to suffer because of the CGD1. And other issue that we also figured out is the conflict between the swing and the gain and the noise. So, if you are going for low noise design, then once again you are targeting larger L for M5 and smaller W by L for M4, and that means that you are going to have poorer or much significantly larger overdrive voltages for M5 and M4, and that is going to reduce my available swing over here. Same thing on the lower side, I would like to have lower W by L for M3, larger L for M2, and both that is going to reduce the headroom on the negative side and going to impact my swing. So, lower noise is going to impact my swing in a negative fashion. So, that is another trade-off we should be aware of. And from the point of view of gain, as we said, the gain ultimately depends upon the GM and the RO products. Now, RO, if we see, is coming as GM RO times RO of this particular device. GM again depends upon the bias current. Noise also depends upon the bias current. So, increasing the current in the first device is going to help us in increasing the gain. It is also going to help us in increasing the or reducing the overall input deferred noise. Here, if you increase the current over here, of course, it also reduces the RO of M5, but that can be compensated if you are having a larger channel length for M5, significantly larger channel length for M5. So, at least for the noise, definitely I would like to bet on the I1. I need sufficient I1 so that the noise input deferred noise is reduced, and at the same time, what we discussed was, if you are reducing the I in this particular stack, that is also in a way going to help us in reducing the input deferred noise, because we saw that the ratio I2 upon I1 or GM2 upon GM1, that was also helping us in reducing the noise. So, these are the factors we should be aware of while doing the design for low noise, and make sure that while doing noise optimization, going for lower noise, we are also meeting the required specifications for the gain and the bandwidth. So, as next step, now since we have done this analysis for noise, frequency response, swing, etc., we will take couple of examples where the design steps will be shown algorithmically, that okay, given a design specs at the higher level, how do you come back to the transistor level design, and how do you approach the sizing of these different transistors step by step in a logical fashion, considering all these constraints, considering all these design requirements in terms of specifications. So, while addressing these specifications one by one, starting from say bandwidth, starting from the gain bandwidth product, which is ultimately dictated by the higher application, like we have discussed that the chopping frequency is going to mandate higher frequency, that gives us the bandwidth requirement, and the precision requirement gives us the gain requirement. So, gain bandwidth product is coming from the higher point, and from there we can see how the gain bandwidth product is defined in this particular amplifier. So, we have seen for the 2-stage op amp how does the gain bandwidth product get defined. It is defined by the GM upon the CC. So, the GM upon CC is the starting point. If you need to set a particular gain bandwidth product for the amplifier where gain is set to be 10 to the power of 4 for meeting a required accuracy, bandwidth for meeting a required chopping frequency, we have this gain bandwidth product being determined by GM upon CC. That becomes the starting point, and then you have the overall bandwidth or the cutoff frequency being determined by the RO of the first stage, basically the P1 is determined by the GM times GM RO times CC and the RO of the first stage. So, step by step, considering these constraints, we can figure out the dependency of the sizing and resolve the design steps or resolve the sizing required for the different transistors in the first stage, in the second stage. Likewise, in the cascode also, we can start from a given specification and tracing back, try to find out the dependency of each of these specification on the transistor sizes and try to set a compromise. So, generally analog design happens to be iterative. So, once you set the transistors to meet a certain specs, some other specs may get violated, and again you may have to go back and look at the design in iterative fashion, fix some other specs, again some third specs can get violated. So, it may take several iterations to arrive at the design which is meeting the given set of specifications within a reasonable margin. So, we will take two such examples, both with the 2-stage op amp that we have spent enough time on, and also the folded cascode, and that will facilitate that will help you in arriving at proper sizing. So far in simulation assignments, I have not asked you for going for appropriate sizing of the transistors. I have just given some starting sizing, starting point for the sizes, and I have asked you to compensate those and get the loop stable. So another important factor is the sizing of the transistor that we will arrive at looking at these concepts, involving all these concepts, and looking at the dependency of the sizing on all these analysis. Any question before we close?
Finding out the noise, we were taking only the differential pair. So one side of the differential pair we have taken, so the input referred noise that we have got with the differential input. So this same input referred noise with a negative sign should be applied to the other gate terminal, then only this will be amplified. So
no, input referred noise means you are having a RMS value of the noise. You are determining what is the RMS value of the noise and what is the frequency content of the noise. So that same magnitude of noise can appear at any of the terminals. So what I discussed was ultimately if both the input devices are having certain noise and we are considering only the differential component of that noise. So noise are uncorrelated at both the gates and they are random, and they are having a wide frequency range starting from low frequency to high frequency.
Noise must be exactly negative of this noise now to get amplified.
Why? Any arbitrary signal at the gate of differential amplifier V1, V2, you can break it down into differential component, common mode component, differential component gets amplified, common mode component gets suppressed. So not only the last topic, even previous topics you can just go through very quickly, and if we have any issues we can discuss.